hardness does not affect wheel wear. There you go.
Okay, Peter.
Reducing the heat-affected zone width is obviously going to improve the performance of the weld, but as I said in my talk, you also need to consider effects of narrower welds on other aspects of weld performance, so it's not necessarily as straightforward as that.
Okay. Next.
We recommend 2% online heat treatment and allowing to divide three different compression balancing rail. The test shows the online heat treatment balancing rail has good strength and toughness as well performance of CL16 rails, which is compared with balancing rail is better than that with polite rail. Yes.
Okay, thank you.
So from our research, we think it is possible to use laser cladding to repair rail surface damage in practice. But of course, to move forward to this stage, we need to do a really field test. So that would be the future work if we can get the funding from relevant industry.
Okay, thank you. So do we have a question that can cross all those authors? There's one in the centre there.
Yes.
Roger.
Yeah, I wonder then about the laser cladding. You say it's going to be a repair technology. Does it mean then that you're going to do the laser cladding in field?
So yes, as I said, in the field, certainly we need to do more research. For example, here we consider it's like a brand new rail, and the surface is very clear and very smooth. But if you apply in the field test, then the damage will be different. Defects would be different. I think we need to have this proper pre-surface treatment, and also because it's uneven this depth, so therefore we need to control the number of the clays, number of layers, and also need to make it to profile the rail.
Can I ask a question? Sorry, nobody's done this before on the stage, have they?
I was going to add something.
All right, sorry. Go on.
I guess a bit of background is that the company industry partner that's involved in this had actually been involved in some field implementation of laser cladding, not on this particular rail grade, but another rail grade. And one of the challenges was actually controlling the thermal conditions associated with the cladding process in the field. So that, particularly for premium rails where you really have to rely on preheating and possibly post-heating to get the properties you want, we see that as a significant challenge if you're out on track and it's windy and things like that. So it's not a trivial challenge.
Sorry, I just wanted to ask quickly, have you looked at cladding like with like? Because you're looking at very different materials, cladding different materials to the rail. Can you do that as a repair, or do you need to clad with the same material?
Here in the start, we used different materials on the same rail. Yeah.
But can you clad like with like? Do you think? We've done it with 260, but it changes the properties of the 260 because of all the thermal processing. But you could nearly get it right. Yeah.
So if we do in situ welding of laser-clad bayonetics, is that going to work?
I have no idea. I know nothing about bayonetics at all.
In situ welding is already, like electric arc, is for repair welding. It's already widespread and in the industry anyway.
Okay. Any more questions? Quite a few. So I think the centre here was up first, I think. Yeah.
Yeah, my question is to you, Peter, concerning to reduce the soft zones of the flash spot weldings. How do you think it can be possible? Is it to reduce heat input? Do you have to change the welding process, or is it possible alone?
It is possible. It's a combination of the heat input, which is dependent on the capacity of the welding machine. So if you have a big fixed welding machine, you could obviously do that easier than if you've got a mobile machine that hasn't got as much capacity. Also increasing the upset, and the other aspect that's now being done is to actually increase the forging rate during the upset to try and sort of get a higher bond strength as well. But I think the other aspect we're now looking at is that if you actually forge to refusal, as it's called, you can actually get an undesirable perhaps anisotropy in your crystal structure near the bond line, and that can compromise your bond strength. So, you know, it's possible to overdo it. So you've got to get all these things right.
Anybody else like to come in on that from the authors? No? Okay, so we had another question, I think, was it Daniel there?
So my question is about the laser cladding. So TTCI did some studies about 5 years ago where they tried to preheat the rail and then put the laser clad on top. And the main challenge was keeping the preheat temperature constant during the deposition of the laser clad. And you can design the laser clad material to be from 400 Brinell to even 900 Brinell. But if you can't keep the preheat temperature constant, you end up with martensite. And we ended up putting those rails in the field, and within 2 MGT, the entire clad sheared off. So my comment would be just be very careful with that, because as soon as you get even a small portion of martensite, that's your crack initiator, you know, and that's for field trials.
I think I totally agree with you. That's a good comment. Actually, all the specimens were prepared by hot clone. And during the process, actually, our PhD students, had a few rounds of discussions and tried to observe and how they did it, make sure that they did it consistently, especially try to keep the preheating temperature constant.
Yeah. So essentially, for preheat temperature, we tried to heat with torch and then use the blanket to keep the temperature constant.
Yeah.
And that didn't work. So the only thing that we think might work would be an induction coil that's directly in front of the laser clad, so that you control the temperature before the deposition, because that's critical for the laser cladding process.
Okay, thank you.
Roger, do you want to come in with anything on preheat for laser clad from your experience?
Well, that's probably the main reason we've only done it in a workshop at the moment. We don't have any in-situ machines in the UK anyway, so, but yeah, this kind of information is useful because we're looking at in-situ repair as a future option. But yeah, it's a real challenge, challenge.
Okay, do we have another question? Oh, there's two more at the back there, so maybe right at the back first. Oh, okay. Yeah, go with that, and then we'll move around.
Yes, I would have a question for the first speaker. You have, I think, a very bold statement, because you say high rail hardness does not affect wheel wear for typical contact conditions. Should we then conclude that the majority of the contact conditions are not typical?
Sorry, saying should we consider...
Should we not conclude then from your statement that the majority of the contact conditions are not typical?
So you're saying that what I've said is wrong?
No, not at all. I just consider that to be a bold statement.
Yeah, I suppose typical is relative, isn't it? I don't know. There will be situations where they're not what we tested at, that's for sure. Yeah.
Are you basically saying that it doesn't make sense to develop new or harder or more wear-resistant wheel materials?
No. Do you need to? I don't think so. No. I've got heads shaking around the room, so I'll go with that. Yeah. No.
Okay.
Let's just up the rail hardness, and we should be all right, because it reduces the system wear, so that's a good thing.
Okay, let's try and get two more questions in. So there was somebody on the back row there.
So I have two questions for maybe the first and the last speakers about the thickness of the clad layers that you tested, that you produce it, and that you tested for the wear resistance. And also, the second is, do you think that there is an optimal thickness of this layer, or for this layer and heat-affected zone and substrate that can be used or defined? My second question is for the second speaker, and you talked about the microstructure inhomogeneity in the world. But and in your model, finite element model, you tested the rolling contact. But in the track, we have also, as Mr. Steinberg showed, we have geometrical also irregularity, and sometimes we have impact. So can you comment on that? Thank you.
Okay, so I think we got...
So to go first. So on our twin disc...
thickness,
Yeah, so twin disc specimens... Yeah, so we use about up to 2 millimeters thick on our twin disc specimens. We use the same on the full scale specimens we've had clad, but we think actually realistically we need to go higher. Our chairman can actually answer more questions on that because he's doing some modelling at the moment to work out what that optimal thickness should be.
I think if you talk about the optimal thickness, of course, first we can change the thickness. One way is through multi-layers, yeah. But then if you talk about optimal thickness, I think depends on what you want to achieve. For example, if you change the thickness, the residual stress level will be changed, and the tensile stress of peak tensile stress location will also be changed. I think this can be also investigated.
Okay, then on the last part of the question, I'm certainly very much aware that the longitudinal geometry is going to change the dynamic loading at the world, and that needs to be considered in any sort of modelling activity. We haven't done that at the moment. I guess that requires a lot more computational effort. We've really more at this stage concentrating on the material characteristics, and because we're particularly looking at rolling contact fatigue, we would also need to look at wear. There is some, I mean, there's other people who are doing modelling of behaviour at World, specifically looking at wear. There's been work done in China, there's some work being done at the University of Huddersfield on that at the moment, which they seem to have a nice model approach for that, and I referenced that in the paper. One of the references is the more recent work from Huddersfield. So you need to sort of model the deterioration as an iterative process, because every wheel that goes over the world is going to change it. And so you need to work out how frequently you need to update that geometry and so on. So it's not a trivial exercise from a modelling point of view.
Okay, thanks very much. Do we have one more? Richard, at the back there.
So, as this should be a discussion, something for Roger and for you. So what we've seen, wear is a system parameter and depends on the softer partner between wheel and rail. So if wheel is soft and rail is hard, and you increase the hardness of the rail further, the wear of the whole system will go down, as will go down the wear of the wheel. If you change this relationship, all of a sudden you make the other partner harder, then something else will happen. But I can support this statement under general conditions, or let's say under certain preset of conditions. Let's put it that way.
That's what I said.
Thanks.
I'd
like to add a comment to that, is that if you keep going up in hardness, you run into a problem that you basically have a wheel rail interface that you can't manage because the contact stresses are so high. So you're going to have a spalling damage. So you need to know what the limit is.
So this statement is true if you keep the contact always in the same size, the contact patch, and then compare different combinations.
Okay, I think we're out of time. I mean, there's nothing to stop people carrying on with that discussion after the main meeting, but thanks very much to all our speakers now.